Okay, in this video, we're going to solve the additional problem that I added corresponding to mixtures. And so this particular problem is currently shown. In this particular problem, we have two tanks. The two tanks are both volume of 1 cubic meter. So they are identical volume tanks. They are also well insulated. For the first part, we're going to assume that they're well insulated, they're rigid, and they are originally connected with a closed valve. Okay, on the left tank, there is an equal mass mixture of CO2 and water. And that mixture is at 100 kPa and 30 degrees Celsius. The right tank contains an equal molar mixture of oxygen and nitrogen at 200 kPa and 80 degrees Celsius. As I said, both tanks have a volume of 1 cubic meter. After the valve is open and the system comes to equilibrium, the question is, what is the final temperature and pressure? Okay, the second part of this problem is if the system is allowed to lose heat to a boundary of 20 degrees Celsius, and so it no longer is well insulated until the final mixture is at a temperature of 40 degrees Celsius. The question then is, what is the final pressure and for that mixture? And so what we have in the first case is we have 30 degree on one side, 80 degree on the other side. Without any heat transfer, it's going to come to some intermediate temperature, possibly higher than 40 degrees. And then we're going to allow that mixture, that same mixture, to lose heat. And we want to know then what is the new pressure if we allow it to lose heat and go to that new thermodynamic state. So in order to solve this problem, we launched the test software, and we have in this particular case under our test apps, this is a mixing process. As we've seen before, it's a closed system mixing process. Again, we have two or more different fluids as a general gas mixture, and we're going to select the ideal gas, the N-ideal gas test app, as opposed to the perfect gas that we had before. Okay, so as before, what we're going to do is we're going to make the assumption that our mixture A is what is over in the left side, which is equal mass mixture of CO2 and water, H2O. And so equal mass will keep it specifying as kilograms. And again, all we need to do in this particular mixture is to get the proportions correct. And so, for equal mass mixture of CO2 and water, we are going to say 1 for the CO2, and we're going to add that, and water, 1 for the water, and we're going to add the 1 there. And so now we have our equal mass, as we can see here, and that corresponds to a molar concentration of 20904 and 7096 as our mole fractions for the CO2 and for the water. And again, I'm writing that down in order for us, when we get ready to determine mixture C, we're going to make sure that we put in the right or the correct number of moles. Okay, now again, we don't want this number of moles here. We really just want the mole fraction, or the mole fraction, because we're going to add a certain number of moles to our final mixture. So this is our mixture A. And so when we go to the state panel for mixture A, we know that the pressure is 100 kPa, and the temperature as given is 30 Celsius. And we know that our volume is 1 cubic meter. And so with this in mind, we see that the total mass of the material in this particular tank is 101,453 kilograms. Okay? And so we're actually going to be able to make up our final mixture knowing this amount of mass and the fact that the mass fraction is 1/2 and 1/2. Okay, so now we're ready to go to and make up our mixture B. Mixture B is the right tank, and it's an equal molar mixture of oxygen and nitrogen. So our first two here, and so again, an equal molar, and so I'm going to say 1 mole of oxygen and 1 mole of nitrogen. And so we see that the mole fraction is 0.5, 0.5, and our mass fraction, which we're going to write down, 5332 and 04668. Okay, the first being for oxygen and then nitrogen. And so we want to keep this in mind as we get ready to set up our mixture C. And so now that we have mixture B, we can now go to state 2, which we're going to designate as mixture B. And state 2 has a total mixture pressure of 200 kPa. And also a total mixture temperature of 80 degrees Celsius with a volume of 1 cubic meter. And so now with this specified, the mixture properties and the volume, we see that we have then a mass that's 204,350. And that's our kilograms of mass in the right-hand tank. And so now we have our two mixtures and the two states associated with our two mixtures. And so the next thing we need to do then is to build up our mixture C. And again, mixture C is after we open up the valve, we're going to allow all of the gases to intermix, but we need to now say that mixture C consist of a certain amount of each of these components. And so the way that we're going to do this is we're going to put them in as kilograms. We're going to make up this mixture in mass units. And what we know is that in mass units, our CO2 is going to be equal to 1.01453. That's the total. That's the total mass. 1.01453 times the mass fraction, which was 0.5. And so when we put that in, that's our first amount of mass. It's about 1/2 kilogram. It's half of the total of mixture A. And then we're going to put in our water, and we're going to do a similar thing for the water. It's 1.01453 times 0.5. And we're going to put that in, and we see that we have the same amount of mass. And so this is the equal mass components of the two species in the left-hand tank. By the actual amount of mass. And so it's relative, but it's also the actual amount of mass, and that's the amount of mass of those two components that are in this final mixture. And so then we also need to put in the oxygen and the nitrogen. And what we know about the oxygen is that the total amount of mass was 204,350 times then the mass fraction that we wrote down, 5332. And so that was the mass fraction associated with mixture B on the total amount of mass. And so I'm going to add that. And so that then comes out to be about 109 kilograms, because it was 204 kilograms that we then multiplied by 53%. And then our final component is the nitrogen. And we once again, we know that it starts, the total mass was 204,350 times then the remaining mass fraction, which was 4668. And again, we add that, and it comes in right at a little bit below 1. So this is our O2 and our N2. This is our right-hand tank. And what we see in this right-hand tank is that the mole fractions are the same, okay? And that makes sense that these two mole fractions are the same, because they started out in that previous mixture as equal to 0.5, but they are the same. And here's the masses, and here then are the masses for the CO2. So we've now generated our mixture C. And so now we're ready to go to the state panel associated with the mixture C. And what we know, or what we're trying to determine, is the pressure as well as the temperature. What we do know is that the total mass of this state is the two masses combined, and the two masses combined in the combined volume. And so the combined volume is going to be 2 cubic meters, or as I put it, volume 1 plus volume 2. So we have the mass and the volume, so it can calculate the specific volume. But what now we have to do is we have to set up a process to indicate that there was no work and there's no heat transfer. And upon doing that, then it can calculate the pressure and the temperature. So as before, we go to the process, and our process is going from state 1 to state 2, coming out as state 3. And we know in this particular case there's no shaft or electric work associated. It's defaulted to 0. There's no boundary work because of the fact that they are rigid vessels and there's no boundary work being done. And then finally, because it's well insulated, there is no heat transfer. So this is then the process. I do a super calculate. I now can go back to the state panel, and the state panel then tells me that the final pressure was 148,739, and the final temperature in Celsius is 58.78. And so that is the answer to part A. Now, in order to calculate the answer to part B, or the second part, we still have the same initial mixtures, mixture A and mixture B. We still have the same final mixture, but we're going to set up a new process. And this new process, which we'll call process 2, still comes in with state 1, still comes in with state 2, goes to, when we select state here, state 3, and now in this particular state, we're going to make the assumption that there is heat transfer. And let me back up a second here. And what I'm going to do is I'm going to go and I'm going to generate a state 4. Okay, and what this state 4 is going to be is the same mass as state 3, the same volume as state 3. Oops. Same volume as state 3, but I'm going to leave out, I'm going to now put in what we know about this final condition for the second part, part A, And we know that the temperature then is known as a thermodynamic property for the final state, and that temperature was 40 degrees C, because we know, or we are going to allow there to be heat transfer. And now if I go back to my process panel and I say for this second process I'm going from state 1 to state 2 to state 4, and state 4 is mixture C, and if I say that there's no boundary work, it now figures out that in order for that 58.78 degree temperature to get down to 40 degrees temperature, there was then this amount of heat transfer. Now the problem also stated that that heat transfer occurs to a temperature, to a boundary temperature of 20 degrees. And I'm putting that in just in order to calculate the correct entropy generation associated with the fact that you do have some heat transfer to a boundary that generates entropy as we go from mixture 1 or mixture A, mixture B to mixture C. And so now if I go back to the state panel for this state 4, you'll see at 40 degrees the new pressure, because we lost energy, and we see that the new pressure goes down to 140.3. And so this then is the way that we would go about solving this particular problem, and recognizing that we could either have an insulated situation with no heat transfer, or if we have some heat transfer, the final mixture just goes to a different pressure, assuming that we know what the final temperature is.